Elimination, it's important, I think, to take a few minutes to talk about the nomenclature of alkenes and the stability of alkenes. So, alkenes are named just like alkanes, except we have a different name. A different ending. And there are one or two other aspects of alkenes that we have to consider, but the first rules are identical, right? So we identify the parent chain. Now, the parent chain has to include the carbon-carbon double bond. So, for example, your parent chain, if you have, let me go here, if you have a compound that looks like this, right, you go, well, obviously the parent chain, you might think, well, obviously the parent chain is the longest, right? But no, it has to include the double bond. So this would be the parent chain, even though it's not the longest, all right, because that's a double bond up there. So you identify the parent chain, which includes the carbon-carbon double bond, and then you identify and name the substituents, you assign locants, you give the carbon-carbon double bond the lowest number possible. We'll do an example in just a minute. And we use the numbered substituents before the parent name in alphabetical order. And we ignore prefixes except iso. We ignore the prefixes in parent names. For dimethyl starts with an M, for example. And then the carbon-carbon double bond locant is placed either before the parent name or just before the -ene suffix, and we'll look at an example of that. So let's look at this structure. This would be pentane, right? 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, okay? So it's the parent chain that has the double bond in it is pent, so we say pent. And when I'm doing this, if I'm not thinking real clearly, I'll do this. If I'm not thinking super clearly, I'm going to go pentane. And I'll just change that to -ene, right? And the double bond could be there, could be here, could be here, could be anywhere, right? So we have to say 1-pent-ene or pent-1-ene. Both of those names are acceptable. Pent-1-ene or 1-pent-ene. And as I said in the previous slide, the parent chain has got to include the double bond. So here's where 1, 2, 3, 4, 5, 6, 7, 8. So this would be the longest continuous carbon chain is 8. However, the longest continuous carbon chain with the double bond in it is only 7. So we're going to say heptene. Okay. Another example, we identify and name substituents, assign locants. This is an example of how the double bond has got to have the lowest priority. So we're going to call this, we're going to number down here because the double bond is closest to this end. Even if you were numbering all the substituents, you would say, well, most of the substituents are here. You might be tempted to start with the 1 here or here to give the lowest number of all the substituents, but that's not how it works. The lowest, the locant has got to be, forgive me, the numbering has got to be established such that the double bond gets the lowest number. All right, so in this case, we list the number of substituents then. This will be 2-heptene, right? 2-heptene, there's my 2-heptene, right? And then I've got a 5,5,6 trimethyl heptene, or as I said in a previous slide, you could say 5,5,6 trimethyl hept 2-ene. Both of these are acceptable. This is probably the one I'm going to do in class. Just to me, that sounds less clumsy. So, but if I pull this up, I use my, I'm going to use Marvin Sketch sometimes to check my answers, and I think Marvin Sketch typically does it like that. So they're the same thing. Now, you please note also that this structure is different. Let me draw a different structure. 1, 2, 3, 4, 5, 6, 7, right? That could have been like that. These are 2 configurational isomers. Remember that term, configurational isomers? These are configurational isomers, and we've done cis and trans before, and we've done E and Z before, right? But if this is the structure, this is a different structure where that's a hydrogen, right? And that's a hydrogen, right? So the biggest on this side, the biggest group is the methyl group. On this side, the biggest group is this other big hairball, right? So they're on the same side. They're on the same side. So this would be zusammen, right? Now over here, the methyl group and the big hairball are on opposite sides of this double bond, right? So this would be Entgegen. All right. Now, remember how we've done it before, and in the previous slide I just showed you, right? Really, the important thing is to remember to consider one end of this double bond at a time. The bigger group over here is fluorine, right? It's not the more massive group, but remember we do by atomic number with the Kahn-Ingold Prelog rules, which I gotta write that out as an acronym because I mispronounce it if I say it too quickly. So the fluorine has a higher atomic number than carbon, so that this gets the higher priority over here, and nitrogen has a higher atomic number than hydrogen, so this gets the higher priority over here. So these look like these are on the same side. So this is going to be a Z compound, right? You've seen how to do that before. All right, as we said a moment ago, if the top priority groups are cis to each other, it's Z. If they're across, it's E. Now let's talk about the stability of alkenes. With the alkenes, it's not really super obvious when we're just using letters, right? That this is really much more stable than this. And the reason why is because of steric hindrance. Can you see the steric strain here? You've got these two big here's a big methyl group and a big methyl group over here. Well, if the methyl groups are opposite of each other, then they're not banging into each other's heads, right? So steric strain means two, or is the reason why trans 2-butene is going to be more stable than cis 2-butene. We can quantify that by burning them, right? So if you take these and combust them, and if you combust them in oxygen, and you see that you get 2682 kilojoules per mole out of that, it's obviously not a real big difference, right? So, and if we combust the cis, then we get less, or we actually get more out of that, right? And that's because this is higher energy. So this is more stable, this is lower energy, and it looks like it's only 4 kilojoules per mole lower. But there you go. That's how we get those. All right, I think I'm going to skip that. This is, again, the same thing we showed in the previous slide, that it's 4 kilojoules per mole lower. So alkyl groups stabilize the carbon-carbon pi bond via hyperconjugation, which we've seen before. And so the more stable the double bond, the more substituted it is, the more stable it is. So can you see that we've only have one group coming off that double bond? You've got 1, 2, 3, 4 carbons. But here, if I've got 2 groups coming off of it, one on either side, this is more substituted. I mean, this is more stable. And if it's tri-substituted, these are all configurational isomers of each other. 1, 2, 3, 4, 5, 6. C6H12. These are all C6H12. However, if you've got methyl groups that are, if this double bond is substituted 4 times, this is the most stable. Okay, so the more substituted double bond is, the more stable it is. So in cyclic alkenes with less than 7 carbons in a ring, only cis alkenes are stable. Why is that? I guess I would encourage you, please consider stopping the video now and trying to build this. Try to build this, and then try to build a 6-membered ring in a trans configuration with this double bonds where the double bond is actually trans, right? 1, 2, 3, 4, and then so start out with something like that, right? Where this is a hydrogen, and this is a hydrogen, and this is a carbon, and this is a carbon, right? So build a 6-membered ring in the trans configuration, and you'll see that it's, well, you'll see it's very uncomfortable. Prove that to yourself by building it. All right, and that's all we're going to say about the stability of alkenes. So we've talked about the nomenclature of alkenes, which is much like the nomenclature of alkanes, and then we also talked about the stability of alkenes, and then in our last video for this homework assignment, we're going to get into alkenes, or elimination reactions, even more thoroughly.